So we have Aleksei Krotov from Northeastern University, who's going to talk about manipulating bullwhip. Complex tasks require complex methods. So looking forward to your talk, Alex.
All right, can you hear me well?
Yes.
Okay. Hello and welcome, everyone. While studying motor control, we were so fascinated by humans dexterously manipulating complex objects that we decided to challenge them and ourselves with one of the most exotic tools, the bullwhip. Here's where it stems from. Much motor control has recently focused on locomotion or on constrained arm movements, such as reaching. Interaction with objects offers more challenges, apparently, and has received less attention. The attempts considered mass spring, pendula, cart-pendulum, and other reduced systems. However, humans can dexterously deal with much more complex objects. For example, on a daily basis, you tie shoelaces and make bed. These objects offer rich internal dynamics, and the study of the dynamics, primarily with modeling, might point us at identifying control strategies, or at least at the right questions to ask. So here is the motivation, and we also wanted to open the agenda for establishing new paradigms and new metrics. And our participants used a whip to hit a remote target. This task required full body coordination, concerted movement of upper body and arm, and interaction with the whip. And the whip has nonlinear mechanics and infinite degrees of freedom. Very few studies considered whip movements in the past. Using physical models of different complexity, they showed analytically that the tip of the whip could reach supersonic regime and crack. These studies, however, did only theoretical investigations without data. Let us see what these models could teach us here, where we ask control questions and we have the data. As I said, we challenge not only participants but ourselves. We seek to identify salient metrics that describe the task and can point us at motor control strategies. While it is at least challenging to control all degrees of freedom of the whip, we suggest that the nature of the task and the human actions could make the physics of the whip simpler to deal with. In particular, we noticed that the whip often unfolded smoothly, as you can see here, while it is propelled towards the target. While no cracking was possible in our experiment, this motion is exactly what the previous models with the previous studies modeled. So we employed simple models used before and elsewhere in physics. The whip here is represented as one-dimensional thread that is pulled forward. As its leading end comes to a stop, the rest of the whip folds and unfolds, and the moving part accelerates. Conservation of momentum or of energy could be used to construct the equation of the whip kinematics. And we found the momentum conservation model to agree better with the data. And we also added the tapering of the whip from geometrical measurements of the real whip. We modeled how the peak's speed travels across the whip when the whip is unfolded. The family of such curves is determined solely by the initial speed of the handle, analogously with the release speed in throwing. In experiment, we used markers to measure kinematics of the body, whip, and the target. Participants were instructed to hit the target in rhythmic style, attempting to hit the target continuously, and in discrete style, with the pauses between attempts. We expected here to force the whip and participants into simpler and more predictable manipulation in rhythmic style. And indeed, we saw clear unfolding of the whip in the data as the whip is thrown at the target. Most of rhythmic trials, which you can see in the left animation, show this evolution of whip shape. While some discrete trials in the right animation showed the same pattern, in most of discrete trials, the whip exhibited more complex movement. So how do we compare model and the data? We focused on a small interval in each trial where the whip was thrown at the target, following the peak hand speed. Dealing with the whip speed profiles, we seek to quantify positions of speed maximum. In this exemplary trial, they form a nice ascending sequence. We normalize the profiles in time and in speed, separately for each marker. This way, we obtain the heat maps where black area indicates the traveling of the speed maximum, and the model will later be initialized at the beginning of this sequence. We also noticed that each participant had the whip moving in the same way in multiple trials. So for comparison with the data, we moved to grand average, one for rhythmic, one for discrete style. And the model predictions were also matched with the data. So the model was initialized at an averaged time, and average value of the handle initial speed was used to pick one curve of the family of those. And here we are looking at grand average for rhythmic style, all participants and all trials, and discrete. You can immediately notice how the black area, the maxima, is narrower in rhythmic style. Indeed, it indicates how all the participants in trials behaved made the whip behave in a similar way. And you also can see that this performance agrees qualitatively with the simple model. And the pattern is more complex in discrete style, and the model shows a poor agreement. Numerically, this could be quantified with the norm of residuals, where the less score shows better agreement. Hence, here we confirmed that the whip, an infinitely complex object, follow relatively simple dynamics. Following this notion, we demonstrated how physics of the complex object in a complex manipulation task can reduce to fairly simple dynamics. The next question is how humans can create and exploit such dynamics, especially for control. That means relating these dynamics with the participant's performance and analyzing the task from the dynamic system's perspective. These questions will be partially addressed in the talks of my colleagues Marta Russo and Moses Naud today and tomorrow. So stay tuned at Neuromatch. I'd like to thank my lab members and collaborators, as it is a huge joint work. And thank you all for attending the talk. Let's open the stage for discussion. You're muted, Richard.
Thank you. Don't whip me. Yeah, thank you for the talk. So I open the floor for questions right now. I had a question to start off. So your model of the whip, I was a bit confused because you showed a body with like joints and stuff, but your model is only the whip, right?
Exactly. So in the model, we only consider the whole motivation is to start with the task dynamics, not immediately the body dynamics. So seeing what the object could provide us in terms of control. So in the model, we only dealt with the whip.
Right. Cool. And so you then give it like a hand, like you said hand velocity, but I suppose it's also like something with angular momentum.
It should be, and in complex motion, it definitely is. And in the data, we looked at both the tangential speed and rotational speed of the hand. However, what is remarkable about this model, it doesn't care about rotation and angular speed at all. So this one only deals with the tangential speed. And there is no rotation here since the gravity is neglected and the whole thread is one-dimensional.
Mm. Yeah, I guess it has to do with where the whip is at the beginning with respect to the angle of the motion.
This points, yes, this is a very important notion as it points at how humans can set the initial conditions to make themselves successful in the task. That's why you should really stay tuned for Marta and Moses' talks.
I see, cool. And so it's kind of interesting, this tapering. Did you, is there any specific tapering that would work better than others? Like, did you have to explore f of x? to recreate some of the properties that you've been seeing experimentally? Is there an f of x that makes it a super whip? Like, are the real whip optimized in that sense?
That's an interesting question. Anecdotally, I can say that it was much harder to crack or to manipulate a homogeneous rope as compared to the whip. And it was also much harder to manipulate the whip, holding it at the tip, inverting the whole mass distribution. I'm not yet sure whether a particular kind of tapering is important, but looking at a few whips that we had, the tapering is close to linear. So the radius, the dependence of radius on the distance from the handle decreases almost linearly. Slightly, it looks like quadratic, but we use the linear approximation.
Interesting.
As of now, it's an interesting question that you ask, how important the tapering is. I got to note it down.
So is that actually data that you're showing?
Yeah, these are the measurements of the experimental whip.
Huh, wow. Yeah, indeed, I'm also in here. Interesting. I had assumed that it was exponential for some reason.
Could be.
So what did your model not capture? You've kind of flashed your result at the end, but I suppose there are discrepancies.
Oh yeah, by all means. So here, looking at the main comparison of the model and the data, we could see that the whole interval captures the movement of the whip from the maximum hand speed until the time of the minimal distance when the whip is the closest to the target. So one thing that the model actually predicts inaccurately is that the whip should fully extend, meaning that forward wave should travel completely to the tip earlier than the whip reaches the target. While in the data, we could see that a process ending later. And another discrepancy is the exact profile of how these maxima propagate. Meaning at the beginning, we could generally see a steeper increase, and then we could see something like an exponential or maybe quadratic growth. Mm-hmm. I believe that has a lot to do with again the stiffness of the whip, which is sufficiently large near the handle, so around here, meaning that the whip here might be moving more as a single piece, as a single object. And indeed, in discrete style, as before in animations, you can see that there is not always that notion of the wave propagating. Like the whip is sometimes collapsed as it's being thrown at the target. Sometimes it is moving as a single rod being swung. The movement is more complex, and the model doesn't capture that yet.
Yeah. So what's actually explaining these like discrete transitions that we were seeing in your discrete data?
The transitions could largely result from averaging across a lot of participants. The first idea of averaging was to have the gross product to compare with the model. However, of course, the refined procedure would be to compare trials or at least blocks with the model separately. So we indeed observed relatively large inter-participant difference. And for example, if you look at multiple discrete trials here,
oh, wow, okay,
this view should be better. You can see the average in the middle. You could see different participants having different profiles. While many of them form the same ascending sequence, for example, the first four on top, you could see others having different patterns. Averaging of those resulted in this discrete, as you said, profile.
Yeah, it looks as though there are two types of motions across participants. Yeah,
exactly. That might point to only two or maybe more strategies for controlling the whip.
Excellent. Well, unless there are any other questions, I think we'll thank Aleksei and all the panelists today for their contributions.